us. Thanks, Peter. Today it's my absolute pleasure to introduce Sabrina James Mielke. Oh, yeah, come on. Come on. Yeah, this will be included in the recording. It's my absolute pleasure to introduce our first in-person speaker in more than a year. So Sabrina is a PhD student at the Johns Hopkins University and a part-time research intern at Hugging Face, currently researching open vocabulary language modeling for unit discovery in a variety of typologically varying languages. While her pre-PhD work focused on formal language theory applied to parsing and translation, during her PhD she published on morphology for language model comparison, stochastic romanization at Google AI, and metacognition and calibration for chatbots at Facebook AI Research. She also co-organized workshops and shared tasks around morphology and typology, and is currently involved in the Big Science Summer of Large Language Models workshop. So thanks, Sabrina, for accepting our invitation and for being here. And everyone, please join me in welcoming Sabrina and enjoying her talk. Thank you.
Awesome. Yeah, thanks for the introduction. I'm going to be talking about like a number of small things today. So this is going to be sort of the usual stitched together conference talks, but I am trying to make it a little bit more fun and include some of the details that were omitted, sometimes a little bit purposefully, from the conference talks. So what I'm going to talk about is first language models. How can we evaluate them? I'm just going to have a short introduction on what I mean by language models. We're going to extend this to translation models and ask some interesting questions about comparing cross-linguistically in those models as well. And I'll close out by giving sort of a proposal, perhaps more of a position paper than the usual We Build Model X paper on how to build an open vocab language model. So let's get started with the evaluation. First of all, we need to decide, okay, this is kind of what we want to be answering the questions. Do current language models work equally well in all languages? And the answer is no. I'm going to take that, put it out there now. We can also ask questions like, okay, well, which of the languages is harder for a current day language model, say German versus English? And maybe we're going to say German is harder. So these are all real conclusions. I'm kind of spoiling them, but I think you hopefully will still get something out of it. And those two questions we answered in previous work. What's going to be new in this talk is, okay, well, what if we go away from the overly exposed Indo-European languages and look at, say, Mandarin Chinese? What about that one? We're going to see it depends. We can also ask maybe if there's something linguistically that correlates with difficulty, and the answer is going to be disappointing. I'll say it now. And finally, the question that I like most about this method is we can ask about translationese. Is it easier or harder? And we're going to find out it's different, but it's not actually easier. So the outline of this is going to be, we define what we mean by difficulty, we look at the models and languages, and then we look at the results and see, okay, is there something that correlates, and do our translationese study. So what is language modeling? Language modeling, the way I use it, is really the old school definition where we say it's a probability distribution over text. It's a generative model that tells us how likely some text is, that we can sample text from. So if there was some sentence like that, kind of abridged for space, often it's just decomposed autoregressively. It's the chain rule. And so you predict each word given previous context. Well, how do you do those predictions? You have a lexicon, a vocabulary, where you have a bunch of units, say these words, the and cat and chased. In the neural day and age, they have an embedding. And then, yeah, you do your RNN or transformers or something, feed in the word that you just sampled and decode like that. So hopefully you've all seen this before. One thing that's going to be kind of funny is what do we do with novel words that are not in the vocabulary? We used to do unking back when, but if we want to sample text, that's not going to be very nice. And if we want to compare it, it's going to be absolutely impossible to use. So solutions great. So say TAE every time, and that's annoying. But this is going to serve as sort of the problem for the last third of the talk. All right, so this is what I mean by language modeling. I explicitly do not mean BERT-style masked language models, because those are not really probability distributions over strings. So how do we measure difficulty? if you've trained a language model, you know that you always try to minimize the loss, and that's the negative log likelihood. Really, you're just trying to maximize the probability of your training text. And this negative log likelihood has a different interpretation. We can also call it a surprisal. And that's really the information theoretic view where we say, if something is very unlikely to happen, if it has low probability, oh, we're going to be very surprised by it. And so this number is going to be very high. And we can express that number in nats or in bits. So maybe this is a sentence, I love Florence, for my English language model. It has some probability under the model, and that corresponds to a certain information content, a certain surprisal, say 5 bits. Now, here's a different sentence in German. Okay, it's a little bit less likely. It has more surprisal, more information content, maybe one in Dutch. And you see, okay, well, yeah, there's more content. The sentences are longer. This doesn't really tell us anything about difficulty, right? We need to somehow make them comparable. And so to normalize for that, what we're going to do, very first step, is only look at translations in this talk. So we're only looking at content that is the same across all the languages for which we want to compare performance. And so now these numbers are comparable. The likelihoods are comparable. And the overall bits contained in an entire sentence are comparable. So if we have a bunch of data in Europol, this is great, lots of data, but very few languages. And we have data in Bibles, which is more languages, all less data. Well, that's true, but if you look at oftentimes the Bible really only means the New Testament, and so that makes it a lot smaller. And in fact, if you really want to look at the intersection of all these languages, like if you align them all to each other, what's in there? You're going to find out that there's nothing shared. So really, there's like a really fun integer linear program solving thing going on in here, where we try to maximize languages and verses that are shared. And that's kind of what we end up with, 62 languages. Overall, we end up with 69 languages, nice, and 13 language families to analyze. Okay, the second issue is I said these scores are all comparable, and that's true, but I chose these scores very specifically to be something that is perhaps not so common. If you've evaluated language models, what do you usually evaluate? Like complexity, yeah, or if it's open vocab, bits per character, something like that, right? We're gonna talk about that on the next slide a bit. But what really matters is that the model has to be open vocab, and we count the total bits. We are not allowed to normalize. What do I mean by that? First of all, we need to be open vocabulary. We don't want to have unks in there. That's kind of sensible because if you have a language that has a lot of, say, morphology or other reasons to have tons of types, well, every time you predict unk, you can cheat, right? And so if I have a Czech language model where like every third word is an unk, yeah, that language model is not going to be surprised by anything because it was like, I told you it was an unk. I'm like, yeah, but what is it? So can we instead of a more subtle point? Here, this word "puch," which is like a coup, in Czech and German, you see it's the same word essentially. But in Czech, it's only 3 characters, whereas in German, it's 5.
6.
So our language model, 6, yes. Counting is hard, that's why I did computer science. So if I have a language model that now predicts them, well, we're going to assume that in both languages, they're equally likely to occur. Well, the bits per character are going to be much higher for Czech than for German. But this doesn't really tell us that like Czech is harder to predict or easier to predict. It's just it's written differently. So really, we just want to look at the overall bits, the overall likelihood of the entire thing. So that's why perplexity and bits per character are not okay. And I mean, this is not particularly hard. You don't even need to change your code. You just get your bits per character and multiply with the number of characters. Ta-da, solution found. So this is just something we need to do to make sure we stay fair. Okay. Well, that was a lot of setup. So what do we do when we have this? Let's take our fully parallel corpus. Let's say this is like a little bit of Europol. We have English, German, Bulgarian, 4 sentences that are aligned across all languages. And now we can train a language model for English, and we train a language model for German, and we train a language model for Bulgarian, all on the same data, all on the respective translations in these languages, so these should be comparable. And we evaluate on held out data. So on this held out corpus, what are the surprisals, the total bits per sentence? And so I kind of visualized that here. It's supposed to mean like, red is more difficult, like more information content, less likely. And you see, okay, sentence 3 seems to be really hard. Maybe that's just a really long sentence. It kind of looks like German is a little bit harder than Bulgarian, something like that. I mean, what we obviously want to do is just sum them up or average them. And okay, now we have something that says, look, German has on average more surprisal than, say, Bulgarian. And so a language model struggles more with German than it struggles with Bulgarian. Yeah.
Sorry, at the beginning you said something about how you're using translations to keep everything. That's true here, right?
Yes.
Does that not avoid the issue? Issue?
So it will still be an issue if you imagine imagine a hypothetical English where every word is ended by 10 underscores. Well, that's going to have very low bits per character, right? Even though it's not any harder than the other one.
What I mean is that if you've translated everything, so let's say we translated it into German, right? And we're comparing German and Czech. So Putsch is spelled P-U-T-S-C-H in German, and then the translation of Putsch in Czech is also spelled P-U-T-S-C-H, right?
No, so that would then be P-U and then C with the...
Wait, I don't understand what you mean by that you're using translations.
This is Europol data. So in one of the sentences here, let's say the first one, resumption of the session, let's say it was originally spoken in English. And so you have a German translation, Wiederaufnahme der Sitzung, and you have a Bulgarian translation.
Oh, I see. The point is that the corpora are all mutually translations of each other, not they are.
Yes, we have information which will move the native sentence. Let's go hand when we want to look at translation. These all translations, it's like a multi-text situation.
Thank you.
Sorry if that wasn't clear. Okay, so this is the data we want to use. If you've worked with Europol, you probably have seen resumption of the session a bunch of times.
Question. So these are all character models. That means models are going to get probabilities per character when it's generated.
Not necessarily. I'm going to talk about that, I think, in 2 or 3 slides. The character level model is sort of the obvious solution to the open vocabulary, but even a BPE level model is open vocabulary, and so we can use both of those. And since we do not want to normalize per character, but really want to have the overall loss, which just sums over all the things, character and BPE are actually comparable.
Okay, so the BPE vocabulary for English is gonna be different than BPE for German.
Yeah. These are completely separate models for each column.
Got it.
So
just summing them and not normalizing them, meaning by normalizing, usually dividing by the length. Right?
Exactly. And so if you divide by length, it matters whether you do characters or BPE units.
Correct.
Exactly.
So because we're not normalizing them, are there any extra care we need to take for creating vocabularies? Which have, let's say, English vocabulary is 8,000 BPE pieces, German is 100,000 BPE pieces.
I'm just going to ask you to sit on that question for a few more slides and then get back.
Okay, thank you.
Awesome. So let's just imagine these are character models for now, or anything open vocab. And yeah, we sum them all up. This corpus, the German corpus has this many bits overall, etc. Okay, we can make comparisons. Everything is great. But I want to make our life a little bit harder. What if the corpus was partial? What if we didn't have all of the translations and some of the translations were missing? Well, now we obviously cannot sum them up anymore, because if we did, well, English would look laughably easy just because it's missing the difficult sentence number 3. And so what we're doing is have a probabilistic model that explains the observed surprisals as a product of an inherent language difficulty, which is going to be a variable that we seek to optimize or marginalize over, to sample, and then in sort of intrinsic information content of the sentence, sort of like what are we trying to convey? And so then we say that the surprisal is really just the product of these two things. Classic mixed effects model, put some log normal noise on it, and now this is probabilistic, and we can perform inference, we can do map inference, sample, whatever you want to do. And in fact, it gets even worse because our actual model is heteroscedastic, which is a word that I learned while writing this paper. And I'm just going to tell you right now, it makes absolutely no difference at all. Even the simple model gives you the same result as the heteroscedastic model. Even the averaging that I showed you before when we had full data Same thing as the super fancy model. So this is one of those slides that was not in the conference talk. And I was very upset to have wasted half a year of my life. But I learned the word heteroscedastic, so it was all worth it. We also tried to put some priors on this, do some Hamiltonian Monte Carlo sampling of this model instead of just doing map. Yeah, no, nothing really makes any difference. So that was a bit disappointing. I learned a lot, but it was a bit disappointing. So paper had a long appendix. All right, so this is kind of our setup for difficulty. Let's talk about the models that we're taking a look at. So as I said, a character level model is sort of an obvious choice. It's definitely open vocabulary, but you can also do BPE models. And those too are open vocabulary because you can always back down to characters if you need to. But now the question of how many merges you can have comes up. And so you could compare, numbers of merges, vocabulary sizes for BPE models. And so that's what we started with, in fact, and took a look at for all the languages. So these are all the colored lines in Europol. How many merges are we going to have? No merges to as many merges as there are types in the original vocabulary. And we see that, okay, no merges is kind of bad. And then for different languages, different things are optimal. Like for Hungarian, you can see it's good to have a sort of small vocabulary. And then for other things like for English, I can't even find English anymore. Oh yeah, it's the black line here. It's good to have a large vocabulary. Okay, that's kind of interesting, but it kind of makes our life hard.
Sorry, what is the y-axis measuring?
The y-axis is measuring the difficulty. So this is, again, just total number of bits in this case. And so we would like total number of bits to go down because, well, then the model is less surprised by the held out data. So that means it was better able to learn the language. So lower is better. And so that's why for Hungarian, having not so many merges is great. On average, for all the languages, okay, well, maybe about here is kind of good. So we're just going to use that for the remainder of all the results. And you might say, whoa, but this is really different now. If you care, take a look at this plot. This is using the same number of, it's the same ratio of merges for all of the languages. And this is using the best for every language individually. And on the y-axis, again, we have these difficulties. And you see that they're sort of the same. It's a much bigger difference between those two BPE models and the character level model on the right. So overall, we're just going to say, fine, we're just going to take this one and ignore the individual optimizing one just to keep it simple. All right, time for the main results of the paper. This is going to have a lot of things on this going on. What we want to show in here are the difficulties of the languages that we get. And on the x-axis, we're going to show the difficulty using the BPE level model, and on the y-axis using the character level model. And so if we put in the diagonal, this is going to put some languages on the easier with BPE side and some languages on the easier with character side. So let's put in our Europol languages here. This is kind of what it looks like. I want to highlight German and English. We can see that German is harder than English, both with BPE and with character level models. And we see that things kind of cluster around the diagonal, which makes sense. But there is still some difference. Like English seems to be easier with the character level model, German easier with the BPE level model. Whether you really want to believe these things, I'm not sure. In particular, once we now go to the Bibles, we can look at something very interesting. So this is going to have a lot more languages in a second. But for now, I only put English and German in here. And you see there's like a bunch of points for English and German. Why are there a bunch of points? What are these?
Different versions of the Bible?
Yeah, different translations. That's right. So especially for English and German and other very high resource language, we have a bunch of translations. And so here we can sort of test our hypothesis. Are we really measuring something about the language or something about the writing style? And as you see, like the German Bibles, for example, they really are kind of all over the place. So some German translations seem easy, some seem hard. But nevertheless, at least the general conclusion that German is harder than English seems to hold in here, right? And so this is a nice way to kind of get a sense for how much variance there really is in the setup. Like it is a very noisy process, but I think there are some conclusions that you can draw. All right, putting in all the other languages, there's a bunch. They kind of cluster around the diagonal. We got a funny one over here, which is Mandarin Chinese, which is a lot easier with characters. Like, okay, big surprise. Characters are already meaningful units, so that's great. But it's kind of cool to see that emerge here as well. Okay, so this is nice. We've got a bunch of points now. Can we actually say something about this, right? We wanted to ask, is there something that makes a language hard? Is there something linguistic, something typological that correlates with that? And so that's what we're going to look at next. First of all, what about morphology? It's kind of what we had in a previous paper, this hypothesis. But if we put morphological counting complexity, so really just the number of slots in a paradigm, it's a very crude measure on the x-axis and the difficulty on the y-axis, I don't see any correlation here. Not really. We can look at some of the walls features, the World Atlas of Language Structures, something about morphology, nope, nothing. Subject-object verb order, nope, nothing. Head part of speech entropy, which is something that was proposed when we wrote this, nope, nothing. Average dependency length, we had a lot more hope in, and indeed, we did find correlation, but since we tested so many things and have to adjust significance levels for that, it's not significant. So if you want to try and replicate this one. You might get lucky, but it's not great. So this is very disappointing. What we did find, however, is some other correlations that are very striking, and that's if we take the character level language models, just the raw sequence length, the number of characters in the held out data, is a great predictor for difficulties. So a character level model really finds the Czech putsch easier than the German putsch. That's kind of fun, and you can hypothesize maybe it's because like mass leaks out every time you have a softmax, something like that. But it kind of is, I think, one motivating factor for why characters might not be the be-all, end-all. And the other thing we found is that the raw number of types we had before doing BPE still determines the difficulty that the BPE level language model has. And I was like, whoa, this is really cool, really interesting. BPE didn't actually eliminate all those traces. And I presented this at ACL, and I was standing at the podium, and literally when I got to that slide, I realized, wait a minute, we had the number of merges depend on the original number of types. We said we want to have as many types as there were before. This influences the number of merges. So of course it stays visible. That one's kind of stupid. I've kind of taken it back since, so that's why I put the slide in there. It was a funny moment. Definitely recommend. So yeah, difficulty, nothing particularly
The second point you talked about, the first point was length is a good correlator.
Mm-hmm.
The second one is, I'm not sure.
The second one really is sort of, I think, a misinterpretation of the results on my part.
Okay.
What we found was that just how many types there were before we did BPE
Mm-hmm.
still influences how difficult the language is with BPE applied.
Right. And you set BPE based on the number of types, right?
Yeah. Which okay, big surprise.
So you mean before BPE, what we have is just character vocabulary?
Before BPE, we still, so in all of this, we assume a given tokenization because the Bibles we have arrive tokenized.
Okay.
And so we treat those tokens as the number of types.
Got it.
So maybe there is something in there.
From the different angle, I think you're talking from before BPE, you were referring to word types. Is that correct?
Yes.
Shouldn't we be starting because BPE starts from character vocabulary?
Sure. I mean, this is the subword NMT BPE, not the sentence piece BPE.
Got it.
So it's starting from words.
But wait, so are you assuming here that there's the same number of tokens per language? Is that in training? Because I mean,
No.
your realization does make some sense if you had consistent tokens, but you don't, right?
If we had it, so it's kind of questionable. Like, what is the actually correct way to do this? If we want to have comparability, should we have the same number of vocabulary units per language, or should we allow some of the languages that have more types to also have larger vocabularies? And we did the latter by choosing to have as many merges influenced by the number of raw word types before. And so under that lens, it's maybe not surprising that, yeah, the number of types influences the difficulty because the number of type influences just the raw number of vocabulary units.
Right. So
Sort of. I mean, what if you calculated BPE on the vocabulary, not on the corpus? You'd get a very different, I mean, that's going to be based on the types, right? But you're actually basing it on the tokens.
Right. This is very normal BPE training procedure.
Right, exactly.
Right.
So the corpus size.
So I mean, at some point, if your corpora get large enough, more data isn't going to change the results of PPE, right?
Sure.
As long as you get like a decent frequency signal, that's all you need. And so these are all still, we train BPE also on these parallel corpora, and so they should have seen similar amounts of text. We just allow a language like Hungarian and Czech more BPE merges, more distinct units, because it started out with more types.
So in your previous result slide, you showed German is easier with BPE, whereas English is easier with characters. And from this slide, what I understand is like sequence length is a strong indicator. That means German is easier with BPE because German is usually longer than English. That means,
is it?
Mm-hmm.
Yeah. Okay. Well, that sounds plausible. Okay.
So I'm trying to take this out to its logical extreme, but I think you can't go all the way. Like the extreme version is, well, what if you just had one character that represented an entire sentence? But of course, then you need an infinite vocabulary, so you can't do that.
Right.
Right. But you could, like, you know, I've seen like the Bible written in emoji before, right? And so, right, like, what if you? I mean, but so that's like, you know, a little bit more extreme than Chinese, right? Mm-hmm. So, I mean, the fact that you're trying to compare difficulty over different vocabularies is kind of bugging me out, right? Like your basis is different in, not basis is the right word there, but like.
Yes, and that would be a problem if we had numbers that were sort of referring to the tokenization. If we reported per character, if we reported per token, right, like perplexity and BPC, then it would really be a problem. And that's exactly why we can't do that. If we have the overall likelihood, it really is just measuring what is the likelihood that this complete sentence as a unit appears in the wild. And then the model, sure, the model goes down and breaks it into pieces and predicts one given the others. But overall, the result is, this is the probability of the entire sentence. This is the bits in the entire sentence. And so that's why we really have this comparability.
Yes, the problem, of course, is that the breakdown, there's more breakdown when you have a longer sentence, right? So you have more like kind of chances for error. More like, you know, you're basically getting more turns. There's more cases where you're not getting a probability of one. And
right, exactly. So, and since these are all softmax models and not sparse models or something like that, that is sort of the hypothesis. In fact, there is probability mass leaking at every softmax. Yeah. Even if, like, after space TH, like the next letter is going to be E. That's what it's going to be, pretty much. You don't need to put probability on the letter X, but you do anyway because it's a softmax. Mm-hmm. So that's sort of the hypothesis there. That's what's going on. Okay.
May I ask one more question?
Yeah.
So, you know, in previous slide, you had a graph where left side, the difficulty takes a dip and then it goes high again. I think maybe before we had a difficulty graph on y-axis. Yes, that's the graph. Yeah. So on the left side, we understand it starts with character, sequence length is long, so it's hard. Yeah. Okay, but when we move on to the right side, sequence length becomes shorter. Mm-hmm. Should have been easy, but something else is going on the right side, and it's making it hard.
Yeah.
And do we have an answer to why is that?
I mean, I think that's a similar enough hypothesis here. Like I don't have any proof of that, but the idea being that if we have more and more merges, we have larger vocabularies, more units to spread your mass over, and that has both sparsity issues and the issue of leaking mass in a softmax. And so that's why these at some point get worse.
Got it.
Okay, thank you. Yeah, these are great questions. This is fun. It's always fun to have an audience that is into it. All right. So yeah, worst possible moments, but we're not done yet. There's more yet to see in this paper, and that's the one that I'm actually really happy with how it turned out. And that's the experiment about what about Translationese? Is Translationese easier or harder than nativese? And so the common assumption is that Translationese is somehow simpler, perhaps structurally, or more predictable than native text, or that there's some sort of signal in there that we can tease out. And so we want to actually analyze that. Let's take the models that we trained, one for English, one for German, and so on, and now evaluate on this matrix of sentences. And now you see why we needed the fancy model with the holes because this one is no longer fully parallel. We have split each language into an original and a translated one. And so, for example, maybe this one, resumption of the session, was spoken in English, so it goes into the English original column, German translated, Dutch translated, and so on. And now with this one, we can once again run our method and get numbers. What is the difficulty of original German, and what is the difficulty of translated German? And so when we compare these numbers, yeah, the original languages seem harder than their translated counterparts. But we missed something. What did we miss? Where's the error? Does someone see what went wrong here? It's really subtle, and it took me like, I think, a day or two until I woke up sweating one night or something like that. I was like, wait a second.
Well, I don't, but I first have a question, which is when you say Translationese, you mean human translation, right?
Yes. So, I mean, these are all paid translators by the European Parliament, because only for Europol do we have this original versus translated annotation.
You have a complete segmentation of the corpus. I don't know if that matters, which is to say that there is no sentence that is in the original that is not in the translated. So there's absolutely no overlap, right?
There is no overlap between any of these, yeah.
So when the question you're asking if we missed something, that means there are cases where original will be easier than the translation is?
Well, I'm saying this experimental setup is faulty. We're drawing a wrong conclusion here. The issue is that I said we're taking the language models that we trained. We trained them all on parallel data, so this was fine. But what did we really train them on? We trained them on mostly Translationese. Because, well, yeah, if you have 21 languages, even English only has less than 20% native sentences in Europol. So the language models are really trained to have an easy time with Translationese. And so it kind of makes sense that they will find Translationese easier than original.
Well, that presupposes that Translationese is its own thing.
It does presuppose that. But I think the fact that we do find a difference here, like a significant difference between the two, and the fact that once we are going to fix this, we no longer find that difference, that's where I would draw the conclusion from that these are, in fact, separate things. But we're going to get to that one slide ahead or so.
So by definition, every parallel data is Translationese. So there's only one source.
Yeah.
Then someone has to translate.
Right. If we had like if we have like a Bible book and it was translated from Hebrew into English, then yeah, this is going to be native Hebrew and Translationese English, and there's nothing else in there. And the beauty of the Europol corpus is that we have this text that is really native in all the languages at some point. So all of the languages have some native component and some Translationese component.
So the solution for this would be, let's say we have 20 languages and 5% of them are native in all the languages, meaning if there was a uniform distribution, would that be okay setup?
Sort of. We're going to do something similar. What we're going to do is we're only going to split one language now. Let's say we're only splitting English. We have English original, English translated, and the rest is still put together. And now we change the training data by removing as many translated sentences, kind of wrong, there should be crossing out a translated one, so that we have an equal number of original and translated English sentences in our training data, right? And the reason we can only do this for one language is we can't do it with all of the languages because this would be too many constraints to handle. I can't have equal things here and equal things there. So we can only do one language at a time. Okay, so we end up with new training data, fully parallel, a good deal smaller than the original, but that's okay because Europol is huge. And now we have as many original as translated English sentences in the training data. Repeat the same experiment with the holes in the matrix, and now the difficulties are the same. And so that's why I said what I said in the very first slide. Translationese, if you believe these experiments, is different because we found a difference in this faulty experiment. But it's not any easier because if we correct for the training data mismatch, the difficulties are the same. All right.
Question.
Yeah.
So in this experiment, it's only original sentences and no translated sentences?
In this experiment, we have as many original English sentences as we have translated English sentences.
Okay.
And then the other columns just naturally follow. So for those, we don't care about the balance. They're going to be mostly Translationese still. We don't care. They're only here so that we can still have the complete model run. We could even do this experiment without these columns, I think, and really only train original and Translationese and then run that on the eventual matrix.
When you say we only have it so the experiments come out, is it because of the fancy model that you're talking about that you need to have this German? Because you're building individual models, right?
Yeah.
including individual models of English original and English translate, but then just one German, one Dutch, et cetera, right?
Yeah. So it is really, we would run into issues because we also need in the model to estimate how difficult an individual utterance cross-linguistically is.
It's that, what did you call it again? The type of model that was very complicated and it didn't matter?
The heteroscedastic model.
That one,
even in the very simple mixed effects model, we have this issue. Even in the very simple mixed effects model.
You still need a difficulty metric?
Where do I have it? Here. Even in the very simple model, we still need this information content for the sentence before it is realized into surface.
It's information content of the sentence across all languages.
And so that's why the other columns serve as tying. And you could imagine, well, maybe we don't do that. It's fine, whatever. But then you could run into a systematic issue when you run this study in the end. Namely, the systematic issue that maybe whenever an English-speaking speaker is talking about something, they're talking about very simple and stupid things. And every time someone else talks about something, they talk about really complicated things. And so then English translator would have much more complicated sentences than English original. And we need the other languages to provide that tying framework so we can see, well, in German, this sentence was a lot harder than here, so probably it is just intrinsically harder. And so that's why we keep the other columns as they are. All right. This is fun. So in conclusion, yeah, it's lots of caveats. Make sure your training rate is comparable and fair if you run these studies. Metrics are comparable and fair, open vocab, no BPC or perplexity, and no p-hacking. It would have been nice to. So this essentially was, in my opinion, a negative results paper of sorts. So I'm really glad we still were able to sell it. But yeah, it was really disappointing not find any relation. Yeah. What are we for time? Okay, 44. I think I'm just going to talk a little bit about the translation models thing. I think we have an hour or so, is that right? And then we can probably chat more about that after also. This is going to be a little briefer and simpler. I think this was a shorter paper. So you've probably all seen this if you do translation, StatMT, blue evaluation matrix. Great, we've got a bunch of blue scores, but kind of this talk is going to start with this very controversial, I know, hypothesis that blue sucks. And not just like you think it does, it's not just a bad metric, but the issue that we're going to look at here is if we want to compare translation models, say we want to compare a model that translates from English to German and one that translates from English to French, well, we can't compare those two blue scores, right? Because blue depends on the tokenization. And so that the notion of words, like this English sentence might be realized like this in Turkish. And so this is only a 1 gram match, whereas in English you get a 5 gram match if you want. So of course, translating into English is going to give you higher blue scores. Does that mean it's easier to translate into English? Not necessarily. Right? And so there might be metrics like character level metrics that sort of deal with this a little bit, but we still run into the push problem with character level metrics. So it's not great. The solution for that is that we're only going to be looking at the likelihood of a probabilistic translation model, which in the neural day and age we kind of get for free, modulo what beam search is doing. But we kind of get it for free. Like what is the probability of the target sentence given the source sentence? It's kind of like a language model, right? Same thing, more or less. So that's the one thing why we don't want to do blue. We want to do these probability scores. And now we can compare again, right? We could do that, but we're going to do something else in this paper, which is we want to tease apart two things. We want to say that the translation process really is translation, like understanding the source and sort of taking out the information content, and then generation, that is realizing this content in the target language. And generation is exactly what we've been doing with our language models in the part before, right? Whereas translation is this weird, fuzzy, leftover thing. How well can we extract information and sort of refine it so that we can generate it nicely? And so what we're going to be doing is essentially say, look, this overall score, it's really a sum of these two components. And we can measure the generation component because it's just a language model. That's going to be the pitch. Let's set this up a little bit more solidly with a bit of math.
So for the translation, is that sort of like in some sense of analysis there? Or?
Something, yeah, something like that. It's
Because translation normally includes
yeah.
generation.
I probably
right?
should have put a word like analysis here.
Understanding?
Yeah, understanding.
Understanding, yeah, okay.
Some rudimentary transformations, perhaps. I don't know. Just anything that's left over when we account for the purely generation aspect of it. So we'll set this up with a bit of math. Okay, we're going to talk about entropies and distributions. Hopefully this is something we're all familiar with. We've seen it in talk before. Surprisal, negative log likelihood. The entropy of a distribution, the uncertainty of a distribution is just the expected surprisal. On average, how surprised are we when we see something from this distribution? And we can also do this with multiple variables. So in this case, this is exactly the translation model case where we want to have the target y given the source x, and all the definitions sort of fall into place. We can again look at the surprisal of the translation and also look at the entropy, where here we're saying in expectation, sampling a pair of sentences, how surprised are we that this target is the translation of the source? And so that gives us this conditional entropy. Okay, so now to put this in math, what I just said in the slide before, what we're going to measure is the uncertainty we have about our target a priori. So really just if we wanted to have a language model just generate some crap, this is just the uncertainty we have about it before. And then we can talk about the uncertainty of the target given the source. And so this should be a lower number than that one, right? Because if we have this source, well, that gives us information about the target. And so we should be less surprised about the target. And so this quantity is positive and has a name. It's called mutual information between these two things. It's symmetric, which is nice, but we're going to lose that in a second anyway, so don't get too happy about it. And it really just tells us how much does knowing the source reduce the uncertainty about the target. And that's what we're going to measure, essentially. We're not just going to measure this sort of like, okay, well, how likely is the target given the source? We really want to measure maybe the target was incredibly difficult. Maybe we're translating into one of those really hard languages like German. Take that aside. We really just want to know what, except for the generation, what about the other stuff? What about the other stuff is more difficult or less difficult? In pictures, this is sort of what it looks like in the idealized version, where this is all one great, beautiful underlying distribution. The entropy is the sum of the conditional entropy and the mutual information. And now when we put models in there, things get a little bit more messy. Because now what we're going to be doing is we're going to say the entropies are expectations with respect to the actual data distribution. So we sample sentences. This is just our validation data. But then the surprisals come from our models, a language model and a translation model, respectively. So this is just standard cross-entropy stuff, cross-entropy and conditional cross-entropy. And we could just plug them in here and say, okay, let's subtract them. It's not exactly mutual information because these are not entropies, they're cross-entropies. But it's something that sort of is hopefully giving the same idea. And so we call that cross-mutual information, XMI. And so that's what we really want to measure now. What is the difficulty in transfer, so to speak? Taking the overall difficulty, subtracting the generation component. So we had some experiments for that. Not a whole lot, not as many as we could, because we didn't have quite as much compute. We just had some models from English into a bunch of Europarl languages and from those languages back into English. And so let's just briefly sketch the results. This is sort of showing what you want to see. XMI across mutual information on the x-axis and blue scores on the y-axis when translating into English. Remember, when we translate into English, blue scores should be comparable, right? Because it's all the same data, all the same tokenization. And so, yeah, XMI and blues correlates beautifully. So that's somewhat reassuring that we have indeed defined a metric that sort of makes sense with XMI. And now the nice thing is we can also do this the other way around, from English into all of these languages, the dark red ones. And there, of course, you see the correlation is much worse because, as I said, blue in the language just means different things because of tokenization. So we have a bunch of plots, correlations in the paper, if you really want to see them. The one that I just want to highlight because it's kind of the title of the paper is this one. There's a lot going on here. All right, let's see what this is. All of the bars are uncertainties. They are all entropies. And so we have this, maybe you can see it, this dashed out line up here. And that is just the language model probability of the English sentence without having seen a source, just a target. And it's decomposed into, well, some uncertainty that we had just because we didn't know the source, and some uncertainty that we had even once we knew the source. And that's what these two bars, this blue and the orange bar, respectively represent. And so what you can see overall here is that these left of the two bars, the brighter one, the one that translates into English, is always lower than the one that's on the other way around, the one that's translating from English into any other language. So the overall, the bars are higher or lower. It's the thing that has both components. If the uncertainty that is reduced by knowing the source, we will see that there's this difference between going into English and going from English. Hence the title of the paper. It's easier to translate, what was it? Translate into English than from English, I think. I might be messing this up. It's been a while. Read the paper. Oh, great. Thank you, Pastor Sabrina. It's easier to translate out of English than into it. If you believe these metrics are meaningful, should you believe these metrics are meaningful? Let's get to that in the conclusions. We also run the same hopeful again. Hey, is there anything linguistic that correlates? And as you can see, there's a whole lot of nope, really. Nothing particularly interesting. We did find like tight-token ratio things somewhat, but it's overall disappointing again. Deja vu. But, I guess that's how it goes. It would be nice to repeat this, I think, with more pairs. So this is really just very few pairs, and they're all sort of into English and from English. It'd be nice to see what happens when we really scale this up to the size we had in the previous paper. And better models, of course. But I think the takeaway from this paper should not be, oh, this is a great new metric you should use instead of blue, because no, it's not. I don't even know anyone should use this metric. But I think it's interesting to think about translation as being sort of this two-stage process latently, even though we don't model it like that anymore, perhaps. But there still is something. We can still tease apart the uncertainty, the probability, into the transfer and the generation part. And we can mathematically describe this transfer part. We can say something about it. And I think that's super interesting to think about. And so hopefully that is what you got out of this paper. Not so much that this is particularly the definition you will want to use for anything. All right, and with that, I was going to segue into the last bit, but we can see how we are for time. We could stop here. This is me on my birthday last year, riding a chair down the street before Hawkins. So, yeah, I don't know. We started a little late. Up to you all, I think.
You can keep on going. We allot till 12:30, including questions, and we've been asking a lot of questions, so you can take over that time.
Oh yeah, love to hear it. Okay, and so let's then take a step back. This is all a bunch of evaluating work, and this is great. It's always easy to criticize people. It's a fun German pastime. But let's actually build some models. So if you recall, we had this slide in the beginning. This is what language modeling looks like. We have our vocabulary, a bunch of units with embeddings. We have our RNN cells, sample one, feedback, et cetera, et cetera. We have unks that make our life hard. We could do characters, but it's just really silly to spell them out. And we kind of want the memorization that we have for the word level vocabulary. So how can we combine those two? And so this talk is going to have this section is going to have a bunch of ideas what the right way to do this is, or what the best way to do this is. I'm going to start by putting the model that we will in the end propose on here. And a lot of the decisions might not make sense yet, but maybe it'll give you sort of an idea. We will have a lexicon of words. And they are spelled out once. What I mean by that is that in a probabilistic model, we say every one of those types in our vocabulary has an embedding, and then we can feed this embedding into a character level language model, and that language model spells out the word. That's the generative story. Of course, in inference time, what that really means is that we take the spelling and the embedding that we have, and we regularize the embedding so that it is predictive of the spelling by optimizing the embedding and this language model. We do that for every one of our every one of our items in the vocabulary, and we end up with an embedding and a spelling, just like we had in the previous table on the previous page. And we do that for what I said, known words. So this is kind of giving you a hint that we are going to have to sort of jump to be open vocab to be able to deal with novel words right after this. Okay, take those. And now the generation process is really straightforward. It's the standard RNN language model. You have your hidden state. You compare with all the embeddings. You do your softmax. You sample an embedding, look up its spelling, blurt it out, and then feed the embedding back to the RNN for the next time. Nothing special, it's normal. Great. What's different now is what happens when we want to have a novel word explained. What happens when we generate a novel word? And now what we're going to be doing is introducing an UNC token in our vocabulary. So this token can be sampled from the softmax, but when it is sampled, we still spell out the word. Now we can use this language model that we had trained to be good at generating the spelling from its embedding. And we feed it, well, not an embedding because we don't have an embedding for the novel word, but we feed it the hidden state because we believe that the hidden state and the embedding should be similar, right? It makes sense here that H1 should be similar to the embedding of the first word because otherwise, why would we have sampled it? And so that's the assumption that we're using here. Using the same language model to spell out a novel word. And you see there's no arrow that goes from this back into the model. So for the fourth word, we don't actually know what we spelled out here. This is a weakness of the model, but it makes this extremely fast and easy to use. Yeah.
Right, so to be clear, you are at generation time. You are choosing among your set of types, which themselves are those embeddings, right, and including UNC, and then spelling out. And you have an assumption here that is there a classifier layer in between the H and the selection? You're not directly taking the H. I mean, the H is not the same dimension as your number of.
Right. So this is sort of overloaded notation. This is, of course, a multi-layer RNN.
Sure.
And so its full hidden state is much bigger. But I'm taking this to mean really the top layer's output thing. So
classification transformation, right?
Yeah, you may just multiply with the embeddings. You could say that's a linear layer. We tie input-output embeddings, so they're just all the same embedding.
Yeah,
and so
it's still a transformation from the hidden.
Yes.
And that itself does not. Well, okay, so you can encourage it to be the same as H. So you basically encourage your well, what do you?
Well, really, we don't do anything explicit, but if we want to make sure that this hidden state leads us to sample the word THE, the way to do that is to maximize the dot product between them, right? Because that's what you do in the matrix multiply. And so if you want to maximize the dot product between two things, what's the best way to do that? Well, they should point the exact same direction and also be as high as possible, but okay, you re-regularize down. But essentially, they should point the same direction. And so that's sort of the idea that a hidden state and the embedding that is most likely to occur in there are probably pointing in the same direction. And so here we can feed in not the original embedding, but the hidden state. And hopefully that gets us a model. Hopefully this language model can still deal with the hidden state because it looks kind of like an embedding, kind of. So yeah, that's what's going on.
Is it an RNN?
This is all RNNs.
Sorry, the character bit.
Yeah, this is all RNNs. I mean, for the character level one, it doesn't really matter as long as you can condition an input, which like any neural model is going to do. Yeah. Yeah, this was, we did this before or while transformers were coming out, I think. I don't remember exactly. Started in 2017, 2018, something like that. When did transformers come out?
2017.
17, okay, yeah. Yeah, so this is all RNNs, but most of the ideas really should generalize. Actually, all of the ideas should generalize to any other autoregressive neural model. Okay.
Is this like a hierarchical model? You have first layer of model, not necessarily one layer of RNN, but the lower level dealing with the sentence, higher level, or other level dealing with the characters. So we have to like hierarchical decoding.
In a sense, right? In a sense, that is what's happening. We have this word level RNN and we have this character level RNN. In a sense, that is what's happening. And the way this model is built, precisely because there is no arrow going back here, we can decode them in sequence. We can first do a full word decode, and then fill in the holes with the character level model independently. So that's why this is basically not slower than a closed vocabulary word level model, at the expense of being a little bit weakened, because for this word, we do not know what the unk actually spelled out. So hopefully it's encoded in the hidden state. So that's the model we're going to motivate. Okay, why did we build it this way? Let's see. Oh no, first of all, I have some samples. I've got to show you how great and beautiful our model is and why you should cite us. This is actually sample text from the model. It is cherry-picked, but it came out of the model. And you can see that the gray words are all actually words in the vocabulary, and those typewriter things are newly generated tokens. And you see that these tokens make sense in context. Like this looks like a valid year. Transferred to the WDIC, well, this looks like a fine acronym of maybe a place name or something. So these are all actually sensible things that it's able to decode. Nice, okay. I have an experiment that I think is much more fun, personally. It's my favorite bit about the paper. And that is, we can also do something else. For the words that we know, for the words that we have an embedding for, like cat, let's take its embedding, feed it to the character level model, and see how would you spell the word cat if you didn't know it was spelled cat? And so we can do that and end up with things that look somewhat similar. So the word grounded, for example, these are all not cherry-picked, by the way. The word grounded, for example, gets decoded as stipped, which that's pronounceable. It looks kind of English to me. It has the right morphological ending. It's a past tense verb, looks good. Differ, coronate, okay, well, it's a verb. It's an infinitive form, I guess. And so it kind of puts something that seems to be length, seems to be encoded in the embedding. My favorite one is turning chance into tranquils. I think that's beautiful. Valuables, migrations. There's a bunch more. Like the list went on, I just cut it to this one, primarily because the next one in the list turned Minsky into shit. I kid you not. And I was like, we can't put this in the paper. They're never going to believe us that this is not cherry-picked. So I cut it off here, and it's like, oh, okay, first 7 entries. Okay, so this is great. This is really fun to do. But why was this a principled way of doing things? What was sensible about what we did here? And so we're kind of going a little bit back and putting on a linguist hat and trying to look all fancy and educated. And we're going to look at something that Hackett said in 1960. He had this idea of language being defined by what he called duality of patterning. He said there really are two levels going on. One level in which meaningful elements, so essentially what we would call words or maybe morphemes, are combined meaningfully into sentences. And then there's a lower level in which meaningless units, so sounds or characters in our orthographic case, are combined into these words. And these are very separate processes. The one on top is very, like, there's a lot going on here. There's some understanding, there's some rules. And the one down there is like kind of arbitrary for the most part. Why is cat spelled cat? I don't know, it just happened that way, right? And so it's important to keep those two layers separate. That's the conclusion we draw from this. We want to keep those two layers separate, and that's why we want to have a word level RNN and a character level RNN. The second thing we can take from this is that since this lower level thing is so meaningless, we really shouldn't need access to the individual characters every time we want to use a word. If I want to talk about a cat, I shouldn't have to remember that it is spelled C-A-T. I shouldn't have to compose C-A-T in my head. I should do that once to define it, to put it in my lexicon, my vocabulary, and then I should be done with it. So, okay, what are we going to take from that? This is really important for things like irregular words, like take the word children. It's a plural word. It's really weird, right? Like, it's not childs. Like, this is freaking me out. And if I want to talk about children, I don't want to have to do this freaky composition of characters into this word every time. No, once I learned that it's children, all right, fine, I'll take it. I'll call it children from now on, and then use it just like a regular word. I don't think about this weird composition anymore. Or take these four words here, T-H-E, O-F, like take the word T-H-E. It's really funny if I don't know if you've ever done this, if you take like an English corpus and you look at the most common trigram. The most common trigram is space T-H. Okay, and it's pretty much always V or something like that. What if we now look at the most common trigram on type level? Space TH appears almost nowhere, right? Really only in the, though, this, that, like very few words. And in particular, a novel word, pretty unlikely to start with TH. So that's why, if we want to be able to deal with novel words, if we identify that as our main difficulty, we shouldn't go by token distributions. We should go by type distributions. This is an old insight also, but we kind of putting it here again. This is true. And in particular, this means that character level models are doing it wrong. So this is sort of the specification of the hand wavy, ooh, I don't like to spell out THE again. No, this is exactly what's going wrong. The character level model has to spell out THE again, and so it's going to be really good at dealing with words that start with TH. And that's really useless, because novel words don't do that generally. Novel words are much more similar to what was called hapax legomena, to words that really appear only once in a corpus. And so with a type distribution, we get much closer to that. And so that's why we have this character level trained on the vocabulary, if you remember the previous slide, on the vocabulary, and not on the running text. So character level models do it wrong. They're also slow, but okay. We really want usage and spelling to be conditionally independent given the embedding. That's what we take away from Hackett and all of that stuff. The second thing is going back even further to something that at least I had also heard of before, the arbitrariness of the sign. Somewhat similar, but a slightly different point we want to make here. Yeah, the connection between signified and signified is arbitrary. So in this case, we can say, okay, spelling and meaning are only loosely are not connected in a sense. Cat is spelled cat because bananas are curved. Meaning is not fully predictable from spelling, really. So there's some examples you can come up with, like silly and folly. They're not adverbs, even though they end in ly. So this is again this claim of like, well, look, there are uncommon words, things that are spelled strangely, and yet you don't want to pay that price every time you use them. You pay the price once when you learn them, and then you're good. And so a construction model. So this is another thing you probably have seen. That was popular at the time, to construct a word embedding from the characters, running a CNN over them or something. They're also doing this wrong, because this CNN is going to have to learn all of these things, and it's going to have to use them every time the word appears. Every time I want to write the something, well, the CNN is going to have to learn that T and H and E together combine into the meaning of like a definite article. So the CNN is going to be really good at those things that we just said are useless for novel words. So what we want is to pair those to, yes, use spellings with embeddings, but we don't want to have this construction thing because it fails, or like it's going to be harder for it to learn these exceptions. We only want there to be a loose link of regularization. And that's why we have the setup that we had, where the embedding is chosen to be predictive of the spelling. But if we really want the embedding and the spelling to totally not go together, that's okay, you know? It's like THE, the character level model is probably really bad at spelling out THE. It probably really doesn't like that, because there's only one example in training where it spells that out, and all the other ones that do not start with TH. But that's okay. That's just one part of the loss. Maybe that part of the loss is high. Maybe this is kind of an unlikely thing. That's okay. It's a probabilistic model. As long as the others look much better for it, it's okay to have chosen this one to be weird. And so that's what I mean by allowing for idiosyncrasy. Regularize embeddings. Don't construct them. And so that kind of gives you a sense of why we built this model this way. Now, I should also give you numbers to make sure I'm not just talking out of my ass. We can compare their performance. Now, this is just standard stuff, perplexity, since it's only one language at a time. Lower is better, bits per characters, because we're open vocab. It's kind of common to do it that way. No unking allowed, of course. And you might say, whoa, your model had an unk. Yes, it did, but only temporarily. In the end, we still spelled out the word. So if I give you the model as a black box, you will never even know that I had an unk in there. All right. So what's kind of interesting about this is that we end up still with a sort of hyperparameter that tells us what we should anchor out during training. Right? So how much should we keep in our vocabulary? And just like everywhere else, you get a 2 in that one. It's kind of interesting to see. I don't know if I have the plots. No, I don't have the plots in here, but they're in the paper. It's interesting to see there's like a sweet spot for this as well, and compare this with PPE. So we're going to be looking at the numbers. Okay, we have a character level model as a baseline. Previous state of the art, you see it has a lower bits per characters, which is good, great, good job. And then a BPE level model, which nobody had done before for language modeling at that point, which is really weird because, like, yeah, I had an easy time beating that previous model. And our model, which again improves on that, for English at least, we tried it on a bunch of languages, and on some of these languages, BPE still beat our model. So, you know, take it with a grain of salt. It's not the best model, but it did beat our baseline's previous work and just new baseline of BPE. What we could also do is look at rare versus frequent words. Which ones are we doing well on? Which ones are we doing poorly on? And you see that the character level model is very good with novel words, in a way that BPE and our model are like so-so. But then when it comes to the more frequent words, it is a lot higher than our models, which are allowed to retain, you know, spelling like THE and CAT. So this is not surprising, but this is the gap that I'd really like to close. I would really like to be able to be good with novel words, as good as the character level model. It's somewhat disappointing it didn't quite work out. But well, there's always work to be done. So that's it for this section. Yeah, if you want a language model, this is kind of what we think makes sense coming from theory a priori. Of course, we have all been in the field since, and we know that deeper transformers beat everything anyway, so why do we care about linguistics? Everything is meaningless. But if you don't want to give in to temptation of fatalism, think about this one. And maybe you can build some interesting models with that. And yeah, criminally underused baselines can beat fancy but bad models. By now, I don't need to tell anybody to use BPE anymore. But yeah, model strings by segments, that seems to be a thing. And do more open vocab language modeling. It's exciting if you don't just do deeper character level transformers. And that's enough bashing from me, I think. Yeah.
So with that, I think we can also open the floor to questions both from the remote audience and the audience here.
On that last bit, do you think there's any possibility of understanding the confidence of a model such that you could interleave between, say, your character model and a non-character model, such that, I guess, to get to, I mean, the obvious solution would be if you knew whether you're predicting a novel word or a non-novel word, that you would switch which model you use, right, and try to combine them together. But you'd need to have some kind of prediction of that too, right? And also potentially some, or maybe you could be confident of the model. So
I mean, I could make the claim that this is what we're doing in the sense that the model is allowed to decide whether it uses an UNC or anything else in the vocabulary. And when it uses an UNC, it kind of does go down to a character level model, but it's not really a character level model given the entire history and so on.
Okay.
So that's somewhat different to what you're describing.
Well, if you look at your results, right, like clearly it's not doing that as well as the character level model is at, right? So if you, basically, if you push it to generate UNC at the right time, I guess you could have a binary classifier. Like, is this a word that we should use the character model for, or is this a word that we should use the non-character model for? Like, you don't jointly. You could jointly optimize that too, right? Like you could add that classifier.
Well, you would end up with like it will be a latent variable, right? If you don't explicitly tie it to UNCness, given some threshold you set on your training data, it will be very much a latent model. It should be interesting. It would be interesting to see whether the model learns when to use which one. Let me think. Do I know any work that does that?
Well, you could already evaluate your own model to see whether you're choosing UNC at the wrong time or not.
I see. Okay.
Whether
so you would
more likely, I guess, then you know, and presumably if you corrected that, assuming your character model is good.
Yeah. Okay. So you'd be saying what we could easily do is rerun the top part, and every time there is an UNC, not use this infilling procedure, but the infilling procedure of a character level model running over all the previous generations.
Sure.
That'd be possible. That'd be possible. Yeah. That'll be a lot slower, but it'd be possible.
But even before that, it would be just diagnostically interesting to know
when it does predict UNC.
Yeah, what's the UNC prediction quality of your model?
Right. Does it know that after cat, there's going to be this word cage that is an UNC? That would be interesting. Yeah, I wonder. One thing that is also something you might wonder about while we're talking about all this latent stuff that's kind of tricky with this model that I didn't talk about at all, is that technically we've built a latent variable model, because even the word cat could have been spelled out by sampling UNC and then spelling out CAT. So we're already sort of training this the wrong way by not including that. But we have something in the appendix where we did those experiments and we're like, does it really matter? And no, it doesn't. There's not much probability mass that we're losing, and we're only losing mass.
That really is different from what's it called? What's the name of the stochastic BPE thing?
BPE dropout.
BPE dropout, yeah. Right, it's kind of like that. But there it matters, right? BPE dropout's a good idea. Right? We always use it, right?
So for me, this diagram looks like how BPE works in a sense that BPE don't spell out the frequent words. For example, that would be a single entry. We look up the embedding, we predict the word. We never spell out the if you're using BPE. Whereas when there is a rare word, instead of going to a separate character model, the same model itself, calls or is capable of spelling out the characters. Yeah. So this is a nice explanation for me how BPE works, isn't it? Or how is this different than BPE? So yeah, in BPE, it's just the one model. It's switching between, am I going to use the word or am I going to break it down and generate it in characters? Versus here, there are two models, word level model and
exactly. That's exactly what I would say. That this really is trying to follow that idea that there are two levels of composition, meaningful and meaningless, and we do not want to conflate them. Of course, that's not entirely true, right? Words are not atomic units. We have some morphology. There's some. We have things like phonesthemes, if you believe in those. So there is something. So you might make that point that it is good to blur them actually, which is what BPE is doing. The other thing that this model, again, is explicitly deficient in that this thing does not feed back. We don't know what we spelled out. Whereas with the BPE level model, well, you do know that, right? Because it's just another thing in the same RNN. We could have drawn an arrow in here. It just would have made this whole thing a lot harder to run efficiently and at scale. Yeah.
So if you go back to, I was thinking about in the first part, I thought you maybe were going to answer this in a second. You were ultimately showing no difference between Translationese and native origin difficulty. Right?
Yeah.
Do you have any sense to try what happened with like mistranslation versus those two?
I was going to ask that question. So in the second portion of your talk, you were talking about XMI, and instead of blue, you were evaluating. I think you were evaluating empty models. Now we can ask the same question: are our test sets are Translationese, or is the target sentence in the test set, is it native? Is the setting matching similar here? So let's say we trained English, let's say English and French. It was native English translated to French, and test set, if it is matching the same setting, English translated to French versus French translated to English. I think there was a paper that said
there were papers that were like, whoa, Translationese in the test sets is actually a much bigger issue than you thought. I remember that one.
So if we look at WMT, for example, way beginning, they had just, even though, let's say, English and French and English, they only had one test set for English and French. Yeah. Now they have different test sets, different direction for this purpose, right?
Yeah, I guess there's nothing standing in the way of extending this to the translation models, is there? You would have to just, you could probably cut that corner and just be like, okay, really only again splitting one language, balancing the training data, importantly. And then, doing the same procedure to estimate difficulties. Well, you really, this is still just the averaging thing. But yeah, as long as you also balance your test sets, maybe it'll be fun. Let me think.
You could create your model with an arbitrary, at whatever translation quality you want, right? You just, much like you create in original, English translated, MT system 1, English MT system 3, English MT system.
These are two separate experiments that we're talking about right now, I think, the two of you.
Ah.
I think my understanding was that you were saying do this with translations, and if it also has translations. I think we can do that. We just want to be careful with the balance. And we will probably have to use the same model, the probabilistic model here. So it won't be quite the same XMI, but it will be so we've got to work out the math, but something like that is probably possible. I don't see why not. We just need to work it out. What you were saying is do this experiment, but instead of doing human translated, just put a machine translated. And that will be straightforward enough, I think. If you also then train the language model on half machine translated English, yep. That should be easy enough to do. In fact, I mean, could rerun the same scripts, essentially also train the data.
Well, I guess I wonder. So there's an open question about what happens in the limit. If you had a really terrible machine translation system that just put out period, well, actually it would do really well because it's very easy to predict period. There's a weird middle zone where it would do terribly, probably, right? Because it's like, okay, I'm just going to start translating some random nonsense now. I guess, I don't know if it's telling you anything, but the reason I'm asking.
No, so no, I think that would still be easy because, again, these are only language models, right? They have no notion of source or target.
Yeah.
So, okay, so I guess there is a really sweet spot in which the model has learned to sample uniformly from the vocabulary. That'll be the hardest because you have the highest entropy imaginable. That makes sense to me. You have the highest entropy. However, you also have great match between train and test. So I don't actually know. Yeah. Interesting.
Well, not great. You have a.
Well, if both are sampled from the uniform distribution, it's the exact same distribution, right?
Yes, but there's no predictive quality. I guess maybe there is.
I mean, you can build the perfect model for your full standard distribution very easily. It's just a hard data distribution, so when it will still be hard. So yeah, we'll be interested to see how these things changes as a machine translation model is being trained. And then maybe there's like a human translation, maybe that's an asymptote, and maybe better models reach that. I'll be interested to see for sure. Yeah, if you have some beautiful MT model outputs lying around somewhere, complete Europol data, please, thanks.
You have all of WMT to look at, right? You have tons of those.
Yeah, really, this would just be decodes of Europol data that we need.
Yeah.
I think 2021 WMT for one of the languages they prepared back translation data.
Right, but I would really explicitly be interested in looking at how this evolves throughout training. And so if every step in training we run this whole machinery, it'll be quite a bit of compute, but if possible, and see how that changes. That'll be really fun to do, I think.
One more question. So XMI, the unit of XMI, are they still bits? Because they were about 100, 150, 100 bits.
Yeah. Because the entities are clouds, so expectation and expectations. Yeah, it's an expected statement. It's how many bits are transferred successfully. I think that's a fair way of looking at it.
Upper bound like blue, for example, can only get maximum 100 blue, but here can be.
So one of the things that is tricky about this, and I've kind of tried to hint at it with these blocks not really fitting well, is that if we have these cross entropies, the orange and the blue one do not add up to the full language model one anymore because, that's right. They do add up because the blue one is defined to be that one minus that one. But the symmetry doesn't hold anymore. And it is just kind of weird because these are two different models. Oops. So it would be imaginable, for example, that the orange block would be bigger than the white block. Impossible, very unlikely. That would be a terrible translation model, a model that gets worse by knowing the source. Would it be possible? So that's why XMI is no longer strictly positive.
If we use, let's say, multilingual model, a single model that does two, which is possible, and people are doing it, then will it be still symmetric?
Well, the issue is that this white block really is a language model and not a translation model. The white block really is, imagine you did not have any source whatsoever. So you could imagine if you had a model like, say, T5 or whatever, that you could imagine just not conditioning on anything and using that. So then it would be the same model, but you still wouldn't have the guarantees you want. It would still be possible to have a larger orange block, to have more uncertainty once you know the source than you had before. Right? You could imagine a machine translation model that's so poor that every time it sees a source, it's like, I'm being asked to do translation. Oh no, and it puts its head in the sand and just outputs periods.
Let's say, for example, word bank, from going from English to some other language where in English it is ambiguous, whereas in other language it's not. We have different words for different sense of the word bank, whether it's a financial institution or river bank. So we could see, yes, when we're going from English to other language, English word bank is ambiguous, whereas coming from the other direction, it may not be ambiguous. Okay. So yeah, that proves your point, right? Even if it is the same model, because of, in some languages, a word can have multiple meanings, whereas in other languages, we may have different words for each meaning.
I'm not sure I really understand where this is, where you were going with this, but yeah, no, definitely you're right.
Let's say take word bank in English and translate it to German.
Right.
Right. I assume German has different sense for financial institution versus river bank.
Yes.
Okay. So let's say I'm going from English to German, and my source side has a phrase bank. Then it would be more ambiguous than going from German to English, the equivalent thing, because the meaning should be different.
I see. Okay, yeah. Right.
Yeah, right. So that proves that orange boxes can be of different sizes.
Well, I guess that would prove that even if you had the perfect model, even if you truly had the data distribution and not this cross entropy thing, these two orange boxes could be of different sizes.
Yes.
Yes. 100% agree. Absolutely. Yes, and that is only true here. It is. No, that's true. And if we were in this perfect setting here, this is the perfect setting, no models, pure data distribution. Yes, the orange boxes can be different in size, but only through the white boxes being different in size. The mutual information has to be symmetric. Which is really fun and somewhat counterintuitive to think about. At least I found it kind of tricky when I took my information theory classes, but that's how it works. So that would really then mean that if one is harder than the other, then it means that there's some intrinsic ambiguity. And that's exactly the example you were making. That's right, in the white box. Yep.
Okay, any other questions from? Okay, then with that, I think we can once more thank Sabrina for the great talk. See you all next time.